Okay, so we are going to do more and more and more about series. So, hope you like them. All right, so we're going to talk about what you need to get through worksheet 27, and the first bunch of it is all about the ratio test. So let's remind ourselves, what is the ratio test? Well, the ratio test, you're going to limit as whatever your variable is goes to infinity, and you're going to take the absolute value of your coefficients like this, and you're going to see is that result equal to 1, greater than 1, less than 1. And if it's less than 1, the thing converges. If it's greater than 1, it diverges. And if it's equal to 1, well, what happens? Then you don't know, right? You have to investigate it. It's a borderline case, and quite often in the context of this course, you're just going to have to tell if it's got alternating terms and the terms are decreasing, you can call it conditionally convergent, and that's usually what we do in Calc 2 with that case. That's a very common outcome right there. Okay, the difference with some of these questions is that they involve x's in addition to k. So we're going to kind of up our game a little bit. So for example, we can make some situation. Okay, so we have some numerical pieces, but notice we have a variable in here. So whereas before we were just strictly adding up numbers, we're building up to something really important here. So what are we going to do? We're going to look at this whole bundle as being our a sub n, and we're going to look using the ratio test at that whole thing. Since this is a fraction, I just take the n and hike the n's up by n plus 1, and then the second fraction I flip. Okay, so that's how we would get that kind of situation. Just like so. Okay, and now we can mess around with canceling things out, so we have an extra copy of this piece. So we just get rid of the exponent, make that exponent 1, so you don't have to write it. But the bottom completely wipes out. And then a similar thing happens over here. We get to keep the 2, one copy of the 2, right? And so by magic, we've now gotten rid of the n, so we don't have to worry about that. But we still have to worry about this thing. You want this thing to be x minus 4 over 2. The limit's now gone. However, you do still have to worry about this thing being less than 1. Or, as you know, we said, the equality case, you have to test more carefully. So let's not worry about the equality case for right now. Let's see what happens when we take this and take it to its logical conclusion. Well, what does that mean? Well, this is just literally a high school exercise, right? You can just say, all right, this is x minus 4 is between 1/2 and negative 1/2, and hopefully you can figure that out without too much stress. Okay, now the next step is we're going to have to, except that I did it wrong, of course you knew that that was a 2. Okay, now we have to add 4 to each of these pieces, and so we get 6 and 2. So what we have is an interval, and it looks right now like 2 to 6, but we don't know if these guys converge on the ends. So right now we have the whole open interval, and we want to know if either end is closed. So we're going to continue this question. So far we have this question, and we have a partial answer, and this is how far we've gotten. So we just have to test the 2 endpoints, test 2 and 6. So testing 2, what's going to happen? Okay, you're going to just pop a 2 in there and say 2 minus 4 to the n over 2 to the n. What does that look like? So 2 minus 4 is, actually, we're going to look at it this way. No absolute value, sorry. 2 minus 4 is negative 2. So since it's negative 2 over 2 to the n, this is equal to minus 1 to the n. So what's happening is you're simply getting plus 1, minus 1, plus 1, minus 1. It is not multiplying by a decreasing piece. This thing isn't actually decreasing in that case. It's just a mess. So it does not converge even conditionally, okay? And then we're going to test 6. And since 2 didn't work, I'm pretty sure 6 is not going to work. But we go through the motions. 6 minus 4 to the n over 2 to the n is just going to give us 1, 1, 1, 1. So you're going to be adding up. It's actually going to go infinite. It's not even going to go back and forth between like two numbers. It's actually just going to go infinite. So neither of these are going to work out. And so we're okay to just say, here's our interval. We know that it actually doesn't converge at either endpoint. The 2 had a good fighting chance, but it still didn't even conditionally converge. Okay, so there we go. Okay, I want to give you some examples of how these can work out so you can see a couple of the types of things that can happen. What if you have n squared x to the n and say, I don't know, n0 to infinity? It doesn't really matter where it starts. But what does this look like? This is really going to look like x plus 4x squared plus 9x cubed plus 16x to the 4, etc. That's what it's going to look like, right? So what causes this to converge? It looks pretty bad. It looks like it's going to go off pretty badly to infinity, but it's if x is equal to 0. No, if x equals 0, then f of 0 is definitely 0. So that's definitely okay. What about if x is equal to 1/2? Well, then you're going to get 1/2 plus 4 times 1/2 squared plus 9 times 1/2 cubed plus 16 times 1/2 to the 4th. And the question is, does this 2 to the n in the bottom compare to n squared that's happening on the top, right? So it actually is okay because 2 to the n is much faster than n squared. So this thing is still going to converge. And the way we will work that out is we can go ahead and use the ratio test to demonstrate that this is going to work. So if you said n plus 1 squared x to the n plus 1 divided by n squared over x to the n, this would equal n plus 1 over n squared times just x, because most of these x's would go away. And then what does this do? This is 1 plus 1 over n squared times x. And if you take the limit as n goes to infinity, this is already positive. This whole thing is just going to go to 1, and then it's gonna go to x, right? So you want to know when that resulting thing is less than 1, it means x is between 1 and minus 1, and then of course you have to investigate the endpoints again. We don't know about these endpoints, but we know that from minus 1 to 1 inside the open interval, we have convergence by the ratio test. We can look at the endpoints just a second. Okay, so the endpoints diverge because you're going to get 1 plus 4 plus 9, blah, blah, blah. So that's obviously not any good. Or when x is actually equal to -1, it's going to be minus 1 plus 4 minus 9, etc. Those are not decreasing absolute values. So we just go ahead and do not claim the endpoints, but it's okay. Otherwise, we've got -1 to 1 and just the open interval that converges. It converges there. I want you to think in terms of this radius of convergence can really go 3 places. You can have a radius of convergence can be a number when you have an interval somewhere on open, or possibly it could be closed on one end or both. But you have an interval somewhere on the number line with a center, and your expansion is only valid over a certain interval. And then you have all reals like this, where you can go anywhere you want, okay? Or once in a while, it looks like the thing never works, but you know how mathematicians are. If it works at one point, they're going to say, ha ha ha, radius equals to 0, but it still, your expansion still works at one point, which is really pathetic. But mathematicians think that way. So you really want to basically think in terms of three cases, that your radius of convergence is either a point, all points, or is like some interval. So you're going to think about whenever you see a Taylor or Maclaurin series in the next chapter, or right now we're kind of building up to this, functions that kind of intertwine with these series like this, you're going to think about the radius of convergence being one of these three categories. Sorry about the font here. This is what I meant to write. Just like it's a letter R with an extra bar on the side. That's all. You can just write it however you like. Okay. Okay, so here's another example. What if you have n to the n times x to the n, and then you're going to use the ratio test, so you're going to have n plus 1 to the n plus 1, x to the n plus 1 over n to the n, x to the n, and then that looks messy, right? N goes to infinity. This thing looks positive, but just pop those on anyway. All right, so what you're going to do is you're going to tear this thing apart, and you're going to say, okay, what do we have here? We have some cancellation. We can get rid of, let's see, we can get rid of all but one of these x's. But then what do we do with these n's, right? So you have, so the x is right out of there. That's fine. Okay, so the problem now is, what is this n plus 1? We can put n plus 1 to the n and leave one n plus 1 outside, and then n to the n. So this can become n plus 1 over n to the n, and then an n plus 1 outside. Okay, so what happens when we do that, this piece is, as n goes to infinity, this part goes to infinity. So in other words, the limit of n plus 1 as n goes to infinity, that part is going to go to infinity. So it doesn't even matter that you probably don't recognize this, but I'm going to introduce you to this right now. This is actually a form of e, but if you don't know that, that's okay, because obviously it's not converging. So you can also rewrite that as 1 plus 1 over n to the n, and you would be forgiven if you think it goes to 1 or something. But obviously that's not going to 0. So you probably have a suspicion that this might converge to something other than 0. And so if you didn't know how to look that up, that would be fine, because you would still have enough instinct to know that this thing is going off. So you don't even have to worry about the x anymore, because this piece is already killing this. There's no way this is going to converge. So the whole point of this exercise is to say, ha ha ha, the mathematician says r equals 0. I would just say, like, oh my gosh, it just doesn't ever work. But the mathematician says, it works in one case. When r equals 0, you're good to go. Okay, so that's how mathematicians think, and that's why you get r equals 0, things like that. Okay, so for question 3, we have to talk about geometric series, and we already did this, but I just want to make sure this is fresh in your mind. If you remember, we did this, and then you multiply by r, and then you get something that, well, this is crazy because we multiply by r and it's equivalent to subtracting a. Weird, right? Only works if it converges. Only works if we're following this rule. Okay, so let's go ahead and solve for it. Flip all those signs around. Factor out s. And then s is a over 1 minus r. Okay, so that's what we've been doing. Okay, we've been doing. And what we're going to do is we're going to allow ourselves to backtrack. We're going to go backwards. I can't spell. Okay, we're going to go backwards. There, hopefully you can see that. Anyway, so what are we going to do with that? Okay, so we have an if and only if. We can go back and forth between these two things, provided we're staying with a small r. Okay, right. So now what happens if we have an exercise that looks like this? I'm going to just make this up. We have this exercise. How do we make it fit? Make it fit. So one thing I want to point out is this 1 is non-negotiable. This has to be a 1. And don't worry, you can just scale the numerator and denominator of a fraction so that works. So for example, if you had like 6 over 3 plus x, that's a no-go, so you have to divide every piece by 3. Right now, this one is okay, and you can't use that format. Okay, so you got to always make sure that in the constant on the bottom has to be a 1, or you can't use this process. And so let's continue with this exercise. We can say a equals 2, and r is this piece, but it's supposed to be minus r. So r is equal to minus 3x. Always be careful because in the formula it's a minus. So you have to, if you have a plus in the denominator, you have to introduce the negative. Okay? Now you can just write your series like this. You can say 2 minus 2 times 3x plus 2 times, you can write minus 3x squared, but you know that negative is going to go away. So you can write it just like that. And then minus 2, 3x cubed, and so on and so forth, like that. So that's fair. It's actually harder to simplify it. You can go ahead and simplify it if your particular application is easier to use that way, but it's not actually easier to expand that mess. In fact, you probably don't even want to write it that way. But anyway, the point is you have your pieces, and the important thing is if you want to know your radius of convergence, this part has to be less than 1. You can drop that negative sign if you want. It doesn't matter. The point is x has to be between what, 1/3 and minus 1/3. And again, you have to test the endpoints over here to see if you have conditional convergence on the endpoints. Always, always, always do that. But anyway, you have the radius, which is 1/3. And if the question is about radius, then you're done. Otherwise, you can continue this exercise yourself. But that's the main drag. This is how you deal with the geometric question. And last but not least, a question 4 or question 5 type. It's pretty lighthearted. It's just seeing if you understand what's going on. Let's say you have some series, and these two question types they're always going to tell you where the center is. They're either going to say the center is at, let's say, x equals 7, or they're going to give you the expression and you can infer where the center is by looking at what's going on with it. But let's say we tell you it diverges at x equals, this is the series diverges or it converges at a certain point, right? At x equals 10. We can give you both or either. And then what can you conclude? What can you conclude if this is what's given? Okay, and so what you want to do is you want to think in terms of, okay, you have some interval and the center is at x equals 7. I'm going to march out 8, 9, 10. There's 10. 7, 6, 5, 4, 3, 2. X equals 2. So we have some information. We know it converges at 10. So that means the radius is at least 3. So it has to extend at least 3 over into this direction, but the endpoint may not be included. So even though you know the radius has to be within a certain bound, you don't know for sure when you get to the other side that radius if you're going to get convergence on that outer edge or not. Okay, but we know it diverges at 10. I'm sorry, it diverges at 2. So again, if we march out 1, 2, 3, 4, 5 to get from 7 to 2, then we're going to march 5 in the opposite direction. 1, 2, 3, 4, 5. This is the furthest it can possibly converge to. So because after 12 we are guaranteed divergence because we knew it diverged at 2. So the point is you don't know what's going to happen on the edge, but you know you've set bounds on your radius. Your radius has to be at least 3, and I'm going to imagine this is in the complex plane. Radius equals 3 is your minimum radius, or radius equals, this is your maximum radius, and you get sort of like a donut shape, right? r equals 5 would be your max radius of convergence for this problem. Okay, max rad and min rad. There we go. Okay, so this is what you should be imagining, and yeah, I kind of let that slip. You're actually in the complex plane, and you don't have to worry about that in this class, but if you go on in math, just be assured that everything we just did works in the complex plane, so that's totally ridiculous, but it works, okay? So once you've created these animals, okay, like they will work in the complex plane too, which just totally blows my mind. So hopefully you're okay now with worksheet 27, and I'll see you on the next video.